Yeah? Oh, okay. All right. I would like to thank you, the organizers, for inviting me. This is first time for me in the Southern Hemisphere, so very exciting. And I also would like to apologize I couldn't come earlier and missed half of the exciting talks. Okay, so yeah, there are a lot of buzzwords here, so let's start from the reverse. So one of the things that we have been interested in understanding is, some of the basic behaviors at the cellular level at a big scale. And so to be a bit more concise and precise, let me just tell you what I mean by that. So for example, if you actually look into the growth rate of organisms with temperature, you usually see it goes up, then it kind of comes down. But the important thing is usually, this blue, which I call mesophiles, the ones that usually live at room temperature, optimal. They are optimal around 310 or room temperature. But then you have these organisms that actually optimally grow at a much higher temperature compared to these guys. So this nomenclature will come back a lot, so let me just introduce that. So red is hot, thermophile, they like high temperature. These guys are blue, they like cold temperature. Nothing to do with politics, by the way. Okay. So what I want is, so if I put all this together, what I could actually draw, something like a fitness, in this case, a poor man's way of saying could be growth rate with temperature. And let's focus on the blue one, the one I just showed you, which has a peak around 40 centigrade or something like that. The red one has a peak at a higher temperature. And the question is, something is going on that separates these two species. And that's what I give here with some hypothetical notation called zeta. And my argument here would be, and in most of the talk, would be these things are related to protein physical chemistry. And that's what we'll try to get to for many different problems, okay? So cellular properties, trying to understand in terms of physical chemistry of proteins. Okay. So just to remember this then, and if I'm making this big claim that if these organisms live at high temperature, it has got something to do with their proteins. So let's flesh out some facts here. So if we actually plot the foldedness of a protein, so usually we know what will happen at low temperature, it will be fairly folded. As I increase the temperature, somewhere it will unfold, and let's say for the sake of argument, this happens around 50, 60 degrees centigrade. But now if you take proteins from those organisms that live at high temperature, the red guys, it actually indeed, and these two are, let's say, cousins, indeed these guys melt or denature at a much higher temperature compared to these guys. Okay, so those guys are known as thermophilic proteins. And so indeed at a protein level, you do see there is a difference. And what makes it an interesting problem for us to understand is, oftentimes, if you just take the two homologous proteins, they have very similar structure, yet one will fall apart more than the other, right? So this is a high temperature simulation. This is just to show you the idea, nothing fancy. Same structure, but at high T, the blue one will start to go apart sooner. And this is nothing other than what I showed you in the earlier picture with thermodynamic measurements, okay? And if you look at the sequence level, they also usually have very high similarity. So the question is, indeed, they have very similar structure, they have very similar sequences, yet one can withstand temperature more than the other. So how do we understand that? And this is something very interesting for us. So what we need to do, so we want to ask, did the thermophiles do something to deal with this high temperature? And it's clear their proteins can deal with temperature. And what is, from a physicist's point of view, what we want to understand is if there is a general principle. So we really want to look into not one, but many, a collection, right? So at the proteome level, right? And that's that axis that I was showing you, right? Because it cannot tweak with only one or two proteins, right? It has to, and looks like from some experiments what we have, all the thermophilic proteins are more stable. So how does that happen, okay? So the two important points that I would like to make here is we need to make a large-scale study at a proteome-wide. So we need to do top-down approach as opposed to usual protein biochemistry where we spend, we take one protein and we spend our life trying to understand in the experimental side of it. And indeed, if you want to do something top-down, you cannot start to do at a very detailed level. You have to do some kind of coarse graining, right, which can be used at a high throughput level. So this is where the spherical cow of physicists approach will slowly creep in, okay? Okay. So what we are looking for is something like what I call is a magic sauce. And the idea here is basically, and we will try to find this coarse graining, this high throughput idea using some kind of theory, magic sauce, and it will be tested against experiment. And the important point is these are all, doesn't matter, this is some quantity, let's say, coming from theory, something from experiment, and if there is a line, okay? And there could be scatter because these are proteins, but if we can figure out the line, which comes from theory, that's what we call the magic sauce, okay? And at different levels, we'll be dealing with this. So, all right, so the first thing we want to do, we want to understand this stability issue, right? How these red guys withstand very high temperature. And I'm gonna create a very simple magic sauce idea in a very simple way of thinking first. And what we need to remind ourselves are 3 different key ingredients to understand stability. So we'll have some kind of energetics due to molecular contacts. There'll be some entropy of the backbone, and then there will be also entropy of the water molecules. So if I try to put it together, so in a very simple mean-fieldy way, so basically free energy difference, this is the free energy of folding, so the delta is unfolded minus folded. I have an enthalpy and an entropy term. And then in a very naive way, I would say, okay, so the enthalpy term is number of amino acids. They get some kind of energetics term. That's the G, that's on average. But if I have n of them, so I have a term like that. And for proteins, I also have a delta CP term. So that's how I'll write my enthalpy. And similarly for entropy, I'll also write another term. This is Boltzmann's constant. That's some degrees of freedom. And that also scales with number of amino acids. So that's where the backbone entropy come in. And then this delta CP term will have the solvent entropy part, okay? So if I just put all these 3 things together in a very naive way, so I can say, well, so if it's all correct, then the delta H would be roughly proportional to number of amino acids, and this is to also number of amino acids. Is that true? And based on the data that you have, indeed you can plot all of this. Each point is a different protein. That's the delta H from experiment. That's number of amino acids. And there is a scaling. Again, there's a line. There is a scatter. We are not that interested in the scatter. So from the slope, you can get this factor. From the slope, you can get that factor. And this is very simple, right? Really baby stuff. But I'm just doing this to get some insights now, okay? So if you put all this together, so then you will basically get what's the attractive energy per amino acid for enthalpy, what's the degrees of freedom per amino acid for entropy. And this is very old work. I'm just showing you data from 1997, 20 years ago. So if I get all of this, then I can get across different proteins for which we have data, I can get all these parameters, okay? And they will give me some idea on average about those proteins, okay? So now the idea is, so if I can do this for my blue proteins and red proteins, do I see a difference? And that's the question. So, average enthalpy per amino acids for red and blue, are they going to be different, right? And that's my expectation. So we did this. We compiled as much data as out there. And if we do this all together, then this is what we see. So this is the enthalpic gain per amino acid. And what you see for the mesophiles, those are the ones that live at room temperature. This number is higher than the thermophile guys. So that feels like that the mesophiles, they're actually gaining more enthalpy upon folding. And thermophiles are not getting that much. But then if you look at the entropic part, then what you see is these guys are actually losing more entropy than those guys, okay? So if I just put all this, again, this very mean-fieldy idea, this average idea together in a picture, so a following picture emerges. So for the blue guys, when I fold, I gain a lot of enthalpy, but I lose also a lot of entropy here. What's happening here? Oh, here. Okay. So one picture that can come out is in the unfolded state, maybe these red guys are a bit more compact. So if they're already a bit more compact, so their entropy is a bit low, when they fold, they lose less entropy. But then they can also have already some interaction, so therefore when they fold, they also gain less enthalpy, right? So one picture that comes out of this analysis is, could these unfolded states in the thermophiles, the red guys, be a bit more compact? And people have talked about this idea of residual structure in the thermophilic proteins, and this is basically kind of trying to lead that way, okay? Okay. So the upshot of all this is, although we talk about, and if you go to the literature and the work people have done for these thermophilic proteins, mostly people have looked into the native state. There has been tremendous amount of work on the native state, and that could be important. But what this thing is also telling us is, unlike the structural biology way of thinking the native state, there could be some puzzle in the actually unfolded state, okay? But that's a problem. So why is that a problem? Because how the hell am I going to explore and understand this unfolded state? So as we know, we have this sequence structure function, but now unfolded state could be disordered, so I need to bring that in. And there are experiments that are coming up. Husan talked about issues with frets and all that. You can do all atom on the theory side. You can do all atom, but I think we'll all agree that doing MD all atom to get the unfolded state is going to be a fairly big challenge. And remember, what I want to do is I want to look at it at a bigger scale. Okay. So we want to do something paper and pencil theory kind of ideas, and we want to apply this at a proteome level. Okay. So to understand these principles, if there is a principle, okay? So now we actually went back, and I went back to what I was trained to do as a graduate student, and this is where we'll come back to some of the things that Husan was talking about, and we'll give some background of some theory that we developed, but coming from a very different problem, trying to understand this adaptation principle in thermophiles. So let me just walk you through the basic ideas of this polymer model. So what you have a Hamiltonian, and then you have this term, which is basically nothing but the fact that monomers are connected on an elastic background, right? So that's a connectivity term, we call it. And it's written in a field theoretic way, which actually makes the calculation much easier, believe me or not. So if the idea is, if I am a polymer chain, this is one of my configuration. At any location S, I have a position vector, and you take a derivative of that. So that's like a kinetic energy, if you just want to call that, and think S like a time. So then you can exactly map all the problems like action and all that. And this S is a continuous variable. Okay, so therefore I have an integral there. Next thing I have is, so things are connected, but now things interact. So monomer here interacts with another monomer there. And we have two types of interaction. First one is the classic excluded volume. So there is a delta function, and that's the strength of the excluded volume interaction. And because of location S and S prime, you need to do two integrations there. That's fine. And next thing you have is your electrostatics. Okay, so these are the basic three things we put in. So that's the electrostatic. So now you have all of this mess, and what you can see is these are all functions of RS, depending on the function. How this is for each configuration, right? So your Hamiltonian would be a functional of this. So you need to integrate over this, so you'll get into all these path integral ideas. But there are ways we can simplify this, and what we're going to do, we're going to disappear all of this, and we're going to write this thing as an effective Hamiltonian, which looks exactly like the first term, because after all, it's a polymer, right? So it has to obey this connectivity idea. So you're going to lump all of these things in an effective polymer-like model, where that L was an effective bond length, now it's going to become a renormalized bond length. So all that junk is going to be dumped into here. So there is obviously no free lunch because all that stuff will get buried in here, okay? And what happens in the homopolymer theory is, so this is the excluded volume interaction between two amino acids, which is replaced usually by one parameter. And the charge is usually of one type, either +1 or -1. But we don't want to do that. We want to keep all those things explicitly there, okay? Now if we turn the crank, then like the usual polymer theory, so then one equation will come up here. And I'll just tell you what everything it means. So the excluded volume term just goes in there. So it's a complicated function, and never mind. I'll show you one of them. The electrostatic terms goes in there, and these are all sequence specific, okay? So what do I mean by that? So this is what I mean by that. So ignore this ij for the time being. But that whole stuff has all these 4 elements, but let's focus just on one of these terms, okay? All this says this is charge at location m, charge at location n, so you multiply them, and then there is their separation and some other function of mn. So this really takes into account what sits at location m and n. So if I have different sequence, all these terms would be different, and all of this would be different. So that's how the sequence specificity will come in. And these 4 terms are actually exactly the origin of this Feynman diagrams, basically, where you are looking at an ij and where these m and n sit in, okay? So if you start expanding, this is exactly what you will get. And now finally, the mysterious x guy, what that does is basically gives me the position. So let's say I'm at a location I, amino acid, let's say 5, and let's say that's amino acid 50. You want to find out what's the distance between them, Ri minus Rj, and their ensemble average would be their sequence separation, I minus j, times that x guy which sits there. So that's the meaning of that ij, okay? So now I have all this stuff from the sequence. When I plug in, I can get all of this x, okay? So by doing this, basically I can get some idea of size. So what does this thing do? So what this does is basically what Husan was talking about. It actually tells you about sequence specificity and not just the composition. So to give an idea, if I have 2 sequences like this, so reds are minus and the black is the plus. They both have 25 plus and 25 minuses, but scrambled in different ways. And the theory can distinguish between the two. Okay, so same composition, but different patterning. Okay, so Husan already did the groundwork for me. So if you, so Das and Papu, they created these 30 different sequences with different patterning of pluses and minuses. And when they did, each point in the y-axis is their simulation value of Rg, and the x-axis is from theory. And this is no fitting. This is a prediction. And as you can see, it does pretty well, the theory and simulation comparison. So now that we benchmarked, again, the simulation model, and as Husan pointed out, these are all atom simulation, and this is very coarse grain, right? All you see is plus minus, right? Okay. And yet, they work pretty well. So now we want to come back, and we're going to actually use it for our original problem that we're talking about. So what happens at the proteome level? So now it can allow us to do a big scale analysis. So what we did, from the database, we took 540 pairs of thermophilic and mesophilic, right? And these are orthologous. And so we know the sequence. And because it works in sequence, I don't need the structure, and that's why I can deal with so many pairs. Then we went through our theory, and what we did, we wanted to answer this question, right? If the thermophilic unfolded state is a bit more compact. So what I'll show you is a much more simplified version of that earlier equation in some limit, 0 salt, and all I care is about, let's say, the end-to-end distance, okay? So in that, this side, this x here, this is related to size. The x will be related to size of the protein. That will have the excluded volume term, which could be related to hydrophobicity. And this basically takes care of electrostatics. So if I now calculate this, for each protein, I have a thermophile, a mesophile. I know all the sequence that goes in the formula. And remember that x is a measure of size, okay? Some measure of radius. So if you calculate that x for all the mesophilic proteins, you get a value which is higher than that for the thermophile. So that basically tells me an x is related to size, right? So the mesophiles have a bigger size than the thermophiles. But that's averaged over all the sequences. But if I actually look for a given protein, so of those 540, let's take the 45th one, and then I want to find the ratio of x for the thermophilic one with the mesophilic one. So that's what I'm plotting here. And for all of these, if I do that ratio, then what I see is 70% case, they are on this side, right? So this ratio is less than 1. There is clearly a bias, and 70% case they are this side, which means in those many cases, the size of the unfolded state in thermophile is a bit smaller than mesophile. So the upshot of this calculation basically is telling me for the majority of the proteome at this large scale, based on just electrostatics, the radius or the size of mesophilic proteins is bigger than that of the thermophilic one, right? So this whole idea of residual structure and all that, now we could actually explore this at a bigger scale. Okay, so just to give you an idea and some insight, where does this thing come from? So if I point this out, really the electrostatics is buried in here, and you have seen this term this morning in Hussein's talk. And so we started calling this sequence charge decoration metric. And all it does is, let's take two very simple sequences. So one is when the charges are completely mixed up, then this value is close to 0, let's say. You have less segregation, and then your denatured state would be more expanded. On the completely other extreme, if you have complete segregation, this would be much more negative, and this state would be more collapsed, okay? And that's the insight we are trying to get now applying this in case of thermophiles. Okay, so the point I made now is statics is important for this high stability of the thermophilic red proteins, and the patterning, right? Where do I put these charges? That matters, right? So that's also very important. And I am doing this at a larger scale and coming from the unfolded state side of the story. But of course, in the community, you still have to address the folded state side of it. So then we said, okay, all right, let's also go back. And can we say something about the role of electrostatics, but in the folded state? So, your tool depends on the question, right? So before, we actually had analytical theory, so we could deal with 540 pairs, right? But now we're going to go to all atom simulations. Therefore, the price we'll pay, we can actually deal with 13 is an old number. It will be 12 pairs, okay? So immediately I lose a lot of pairs. But that's the best we can do given what has been done in the field, okay? So it's poor man's way of doing high throughput calculation. So what we did, we actually tried to simulate the folded state. And the first thing we realized, there are loads of issues with convergence. And long story short, we got distracted. We wrote a paper even on how to worry about convergence in the folded state. And the point we tried to make is you need to at least, and none of this previous analysis for thermophiles doing MD for folded state cared about that. So we actually look into number of clusters, their distribution, their entropy to make sure those things have flattened. So just to ensure all of that, we had to simulate quite long. We got this many microseconds of data and 10 terabytes of data, but what the hell we do with that? So then we started to analyze them. And the first thing we did is, because we are guided by now this electrostatic principle, right? So we're going to look into what does electrostatic do in the folded state. So what I'm showing you here is the charges in the structure. And now we're going to find out what's the distance between them, and that's how we're going to define, if they're forming ion pairs. But now because of dynamics, these ion pairs are forming and then dissolving. So these tubes, their width basically telling me how often they're in contact or not. So if I use that, then I have a better way to characterize based on simulation. And the first thing I realize, so we call these edges. Okay, so in thermophiles, you have more edges than mesophiles. This is an x equals y line, and in thermophiles, they're mostly on the other side. Okay, so that basically gives me an idea. There are probably more ion pairs or whatever is forming there in a hand wavy way. But now we can actually calculate, do the electrostatics calculation. So what we do now, we basically do Poisson-Boltzmann. So basically solve this in the protein interior. And these are our 12 pairs. And the important thing is we do this calculation, the finite element calculation, at every snapshot of the MD. So that's costly. But we do it, and if you don't do it, you won't get the results that I'm going to show you. If you just do it based on PDB, the results could be all over the place. So the fluctuation matters. And I don't want you to look into the table per se, but what I'm showing you the value there is the interaction from electrostatics for thermophile in the folded state minus that same interaction for mesophile. Okay? And what you see in most of the cases, these numbers are negative, except these two guys. Right? So basically what's telling you is for thermophile, the electrostatic is contributing more favorably in the electrostatic energy in the folded state. Okay, so that's one part of the story. But we also need to worry about what happens to the desolvation penalty, right? So just because I have more favorable interaction in the folded state doesn't necessarily mean it's going to help me, because I also have to bury charges from unfolded to folded. So the important thing to realize is in mesophile, if I have only one ion pair, but in thermophile, now let's say I have more ion pairs, right? Because I showed you I have more edges. But in this picture, I can do this ion pair formation either this way or that way. And what I'm going to argue is this strategy is better than that. They will both give me the same number of edges, but this will have 4 charges and this will have 3. So in this case, I'm going to pay less desolvation penalty. So that's a bad idea, and this is a better idea. So based on this idea then, what we did, we came up with a new metric which basically calculates the number of edges divided by the number of vertices. Right? So what will happen, that metric would be higher in this case than that case. And if you actually now compare that over the probability of the simulation, you always see mostly the red ones have that number higher than the blue ones. And there are only few cases where they are indistinguishable, but mostly the red is higher. Okay? So again, this shows this connectivity of network of charges is important in thermophiles. And then actually at the end, if you actually put together the desolvation penalty itself, you see the trend doesn't completely alter, but some of the proteins, like this guy flipped, this guy became borderline. But overall, the important thing to realize is, again, there will be 8 out of 12 proteins where this number is negative, which is saying that electrostatics, even after taking care of desolvation penalty, is keeping it more favorable in thermophiles. So that's all of that. So the take-home message from this part, therefore, is although these guys have very similar structure, very similar sequence, it matters where you put those charges and how you put those charges, right? Messing with charges at a first level is what has helped in this adaptation principle to give more stability to the red guys. So now, as I told you, we came up with this whole sequence business and all that, trying to understand this problem of thermophile versus mesophile. But when we did the theory, we realized this could be a key application in IDP, and as Husan has been showing all these ideas. And what we now want to do also, apply this, and because this does not require simulation, it's a very simple metric. Can we say something, would this be a magic sauce for IDPs as well? So what we started doing, we actually started messing with some of these ideas, and we took that theory one step further, and we're going to apply this for IDPs. But what I'm going to do, I'm going to write down here the size of an IDP, the same X metric, which is basically related to size. But now I'm also going to bring in temperature. So my excluded volume term can depend on temperature, right? So this is basically some kind of normalized temperature. And I can use this theory to see how does the size change with temperature. And I'm showing you this is a particular protein from the DisProt database, which is the database for IDP. Uninteresting parts I'm not showing, but the parts where I have pluses and minuses I'm showing. What I'm going to do now, and we did search through the whole DisProt, and there are many interesting cases came out. This is just one simple example, and this is hot off the oven. So now let's look into, where did I make a change? So here, this is not a dash, this is a minus. So I had phosphorylatable site, and let's say I just hit only that site to phosphorylate. What will happen, you'll get the green one, and you'll see a big difference in the conformation. And what's also important, depending on where you are in the temperature, so if you are somewhere there, then this guy can be in the coil state, where this guy can be in the globule state. So this is the classic coil globule kind of transition. Now what becomes interesting is, so what I did, I changed the charge there in the phosphorylatable site, right? Instead of making the change there, if the phosphorylation happens somewhere here, you will get this red curve. So what this is showing is you can actually have hotspots of phosphorylation. And now we're trying to connect this up with biology. And again, depending on where you hit and harnessing this fact of sharp transition, you could actually gain very big switch-like behaviors and differences. And then actually we went ahead and we actually tried to do, again, all-atom simulation from Rohit's lab. And to see actually indeed if I phosphorylate here versus there, does that really lead to big difference in size? And you can see this is some very preliminary results, and indeed the all atom also shows there could be difference in size. Another example, this one I find very interesting for the audience here, is again these two are very similar sequences, very similar pluses and minuses, and only one place. Like here, the 0 became minus, and somewhere there, the other one changed, right? So they have same composition, only the charge changes between one position to another. What you notice is one of them will have a first order phase transition, and the other one will go in a very smooth way. So you can get the order of the transition also being changed. And this all comes because of that analytical theory that we developed. Okay, so that's how we are now trying to take this at a big picture level and trying to understand properties of IDPs, and particularly in case of phosphorylation, because that allows us directly to mess with charges. Finally, let me just tell you one other story. Again, with this magic sauce and trying to understand at a big level, cellular level, trying to understand folding timescales, folding kinetics, and tying it up with this idea of the talk. So as most of you probably know, a long time ago, Plaxco-Baker had this thing. What they basically plotted is the folding rate against this structural quantity called contact order. And just to remind the community, I know some people know this very well. So if you basically have a contact here between I and J, whatever is the separation, put that, sum it over all the contacts, divide by number of contacts, and it correlates well. So that was back then in 2000, and so we always tried to understand, if there is a first principle, this field theory way of doing this. So what we did, we actually went back, we did a full-blown calculation, first to understand why this formula works, and then we actually even tried to improve that formula. So the idea here is the following. So basically, when you are trying to fold, you are going over a barrier, and every time you are forming a loop, you are losing some entropy, and that causes the barrier, right? So if you just use that simple idea, so every time I'm forming a loop, let's say I'm forming this loop, I'm losing some entropy there, right? But what Plaxco-Baker formula does, it assumes all the loops are independent. So it kind of and so it will be exact, when I form a loop here and a loop there. But in reality, it may not be. So what can happen now, if they are not independent, if they're independent, great. You have a loop forming here, another loop forming there, let's say, right? But what if I have nested loops, right? So then you are going to start to get diagrams like this, like that. So this is exactly the Feynman diagram picture then start coming in, and you can do all sorts of these calculations. And then what you find is the following. You recover the original Plaxco-Baker stuff, but now you start to get all these higher order terms because of how these loops are forming, right? And if you start to have 2 loops, 3 loops, so you can get all these corrections. So we can actually improve the formula, and then we actually tested it against all the kinetic data that's out there, which I'm going to skip. So the long story short here is we have a new metric to take into account the structural subtleties into picture, more subtlety of the protein topology. We can predict the folding speed. Then what we did, we said, okay, we're going to apply this again at a large scale. So we took the proteins from E. coli and yeast proteome, for which we know the structure, because this formula needs structure, and for which we also know the abundance of the protein. You will see in a second why. And then we basically used this formula, because this formula needs the structure. Then we run through the theory. We can predict the folding rate, which is here. Okay, so it's 1/time, log of that, for the entire proteome of yeast, for which we had the structure. So this has 750, weighted with abundance. And this is how we asked, okay, so how does the folding time distribution for the yeast proteome look like? So it looks something like that. Okay, that's great. So now we try to understand, why does it look like that? So what we said, okay, so can we come up with a different theory to understand this distribution? So notice that end, that is very fast folding rate, and roughly that number is around microsecond. And as we know, microseconds folder are the fastest folding protein, so that's roughly there. And after that, the probability is going down. So that's the speed limit of folding. Okay. Then what we say, okay, so speed limit of folding, fastest folder, and that's related to some barrier height. So if I fold fast, that means the barrier height is low. So very simple-minded way of thinking. So we say there is a minimum of delta G, dagger. All right. So that's that. But now we notice there is another limit here. So things are not folding anything beyond this side, right? So that's the lower limit, right? That's the slowest folding proteins. Now we say that in between, so first thing we say, okay, so there is one limit there, which is the speed limit. Basically, it's the chemistry or whatever. I cannot make things fold faster than that. And there is another limit here. I cannot make things fold slower than that for whatever reason, which I'll come back to in a second. And in the middle, there is, I say, okay, all these other values of delta G daggers are allowed. So the fitness landscape is flat. There is no other pressure. So if I believe in that, and then what I would say is, now the lower limit, right? So the limit here, where the folding speed cannot be any slower, right? So this is the slow folding in this end. So that means I have a very high barrier, right? So delta G dagger has a maximum. All right. So with these two limits, so one limit on that side, which is the fast folding speed limit, this is the slow limit, they have correspondingly two barrier heights, minimum and maximum. Everything between flat in between. What we can do, we can think of a mutation model, and we can say, well, so mutations are happening in this fitness landscape, and there is a drift. So we can write like a Fokker-Planck or whatever you want to call that equation, and then there is the drift term, there is the random walk term, and there is no other selection, okay? And now you put two boundary conditions. What are the boundary conditions? One is, you say, well, I cannot, for whatever reason, and we'll come back to that, right, fold any slower than whatever is the limit here, which we'll say maybe with some biology or something. And then other limit is I cannot fold any faster than that limit, which is design whatever. So in those two boundary conditions will set me 0. Those are limits. And then if I solve this, then basically what I will get, a function that looks like that. And the shape of the function is this black curve, okay? Ignore the red, that was for E. coli. Let's just focus on the blue, that's for yeast. And so what happens, just remember, the blue curve, I got it in a very different way. I had structures from PDB. I had some polymer diagram-based theory, which I used this PDB structure to predict the folding rate. The black curve, I got really from this mutation-diffusion model. And then it really fits, and this limit that turns out based on this curve is around 7 seconds, okay? So roughly, whatever, 10, 15 seconds, whatever, right? So then we really started scratching our head, and we kind of understand the limit of that. That's chemical physics, physical chemistry, whatever you want to call it. What is this limit that's stopping it? And then we started look into all these other processes in the cell. And what we saw, and this is why I'm showing you this data for yeast, is this is from Erin O'Shea's lab. They measured the degradation time of the whole yeast proteome. And that looks like that. So we think there is the grim reaper of degradation sitting there, which separates and sets probably this time scale that below which you cannot do that. So basically the idea is I cannot beat chemistry. There I have some rate after which I cannot fold faster. Here I have a protein degradation that's sitting there. And in between, now if I have a flat fitness landscape, that will explain sort of this shape of the behavior. So I'll skip that. So basically what I told you is 3 different stories. One is how to understand thermophilic adaptation, and charge is the main story there, and the patterning of charge. How we are using that idea now to IDPs. And here I told you a side story also about kinetics. And all these cases we are developing coarse grain theory to apply at a big scale and understand some principles and some ideas. So these are all the grad students in our group. These are all the undergrads. These are my collaborators over the years, and funding from NSF and Research Corp. And thank you for your attention.